Hi. So this time we are going to emulate some behavior in an APL interpreter, which is to print out arrays. But instead of printing them out one by one, we're going to combine them into a single array, which will look the same. That's the point. So here's some sample data. And, well, if we print it out, we get them next to each other. But if we print them out one by one, instead, then they end up on top of each other like this. And so the idea is we need to generate an array which looks like this when we print it out. And there are a few different approaches to that. I'll just show a few, but when we had the chat session, then we had a lot of different ways to do it, including some very silly ones. Okay, so maybe the simplest way to do this is to split the display of each one into separate rows and then combine all the rows into a single list of rows and then combine them all into a single matrix, and that's basically it. And there are a couple of things we need to watch out for that. So here is a defen lambda, and we take this data, and there are some issues with simple scalars that mess up our algorithms. We can take that in a moment. So we'll start off by formatting each element of the right argument. So this doesn't actually change how they look at first, but this makes them into character arrays. They might be scalars, vectors, or matrices because we don't have any higher rank elements per the specification. So this will look much the same. Now, when we can split each one into its constituent parts, into its rows, which for vector and the scalar is not going to do anything significant. Just try to enclose it. So we split each, and this gives us all these rows. So now we can see that if we are to combine all these arrays here, then we're going to get the rows of our final result. So this is exactly what we're going to do. We're going to do a concatenation reduction. And now they've been combined, but they're also enclosed because a reduction reduces the rank. And we had here a list that's rank 1, so we have to reduce it to rank 0, which we need to unpack so that we do a disclose. And finally, we mix to make this vector of vectors into a matrix. And we get this result. And that is, in fact, a matrix. We can see if we select this, and there are a bunch of headed spaces at the end. This is why it's important for us to format it, otherwise we might get padding with numbers instead. One little thing, kind of style thing, we have two loops here, two eaches. We can merge them to a single loop by doing a top instead. So every time we format, we finish off post-processing with the split, and then we go to the next element. However, there are some issues here, and that is if we have just simple character scalars, then we get the wrong result. This is supposed to be stacked on top of each other. Remember, if we output each one separately, then they go like this. And the problem is that this gives us a scalar. It doesn't change. The format of a character doesn't change. And so when we split that, nothing changes, and then we just merge them all together, and basically there's no change all the way through, all no-ups. We can fix this by making each one into a vector. How do we make a scalar into a vector without making any effect on any other arrays? And there is a trick, and that is to do a replicate. So replicate takes an array on the right and some multiplication factor on the left, and then it replicates the elements here. If we do a 1, then we see no change. But the important thing is that it needs an axis. So if we ask what is the shape of this, it is 3. What is the shape of a scalar is an empty vector. It has no axis. But if we do a replicate on it, then this has to return a vector. Because if the number was higher, we'd have to have a vector. So we're replicating along this axis, the single axis that it has. So this became a vector. But on any other array than a scalar, this has no effect whatsoever. So we can go up here and do a one replicate on each, and that gives us our result. And if we try to do it on our test data, then it looks just the same because one replicate does not have an effect on any other arrays. Okay, this was one way to do it. Another way to do it is to take advantage of APL's default display. And the way we're going to do that is, again, we start off by making sure that our arrays are not scalar, so we don't end up any problems with that. And then instead of just formatting them right away, we're going to stack them on top of each other. So we have a vector of vectors and matrices now. And if we use the monadic comma bar, that is the table function, it makes sure that the argument becomes a table. So if it's a vector, it becomes a column matrix instead. And if we then do a format on this, then APL will transform this nested array with various data types into a uniform character array, and it's going to be a matrix in this case because nothing has higher rank. And well, look, we almost got what we wanted. There's just one issue. There's one space too much on the left and one space too much on the right. But that's easy to fix. There are a couple of different ways. Maybe the most straightforward way, but not most efficient, is to do a transpose. So put the whole array on its side. That looks all very silly. Drop the first row and drop the last row. So that's -1 drops from the rear. And then we transpose back again. And now we've got the right result. So this is one way to do it. Another way to do it would be with the rank operator. So we could say here drop rank 1. That means drop on each row. And we also need this one. We can also combine them into a single thing. So if we make a little tacit function here, we can write it like this. So this is saying the argument and 1 drop from that, -1 drop from that, all of that is rank 1. And that also solves the problem. Finally, we can kind of sidestep this whole issue of combining the arrays into a single array and making them match in their width and so on. And we can do that simply by formatting them and then concatenating carriage returns or new lines to them. So how do we do that? This time we're going to go tacit right from the outset. We'll start off by formatting each one, and this time we're not worried about making them into vectors or higher rank, because we're going to concatenate a new line to them, and then the result is going to be exactly the same. It becomes a vector at that point anyway. So here we have formatted each one. Of course, this looks much the same. So these are now character matrices. We can see that if you try to add a number to them, but trust me on this. And then we want to have a concatenation on each one with a new line. So how do we write a new line in a tacit function? We're going to use the Unicode character set, universal character set system function, and with an argument of 10 for a line feed. You could also use 13 for carriage return. Problem is this messes up our tacit function a bit. Really, we want a fork. We want a left sign here, which is the formatted thing, and we want the new line on the right. And this is a constant. And we could parenthesize this and may use the constant operator. So this derives a constant function, and this adds then a new line to the right on each one. And this will look very silly. Spaced out, this is because we added an extra new line after each row, but they are also already matrices, so we get this double spacing. Maybe slightly more elegant and less efficient, but it looks cool, is to compose these two functions together. They concatenate each with the UCS, and then we have the 10 as the constant function. So now the fork looks like this. We have the left tine with the format each, the right tine is the constant 10, and the middle tine is the concatenate each with the Unicode value of, and then we get that 10 in. So this gives us exactly the same effect, and we don't actually need space there. Okay, so now that all of this is in place, we don't need the structure anymore. We don't need these matrices. We can just make everything flattened out, enlisted, and we can do that with the enlist function. And well, there we are. That's one issue, is that trailing line break here, because we added one to each. So we just need to drop the last one. So -1 drop. And then because this is a monadic function, and we again need this everything to be a fork. So this is one function, which is a fork in itself. And this is the left tine here. So we need this to be a function. We compose them together. So preprocess the drop with the enlist. And there we have it, a third solution to the problem. Thank you for watching.